All right. So now we're going to do a little bit of some examples. So at the end of the last lecture, I had said that the next time we would pick up again, starting from some of the optimization material that was about the constraint optimization, but I've decided to make a little bit of a change. I want to instead go over some examples that utilize some of the things we have already been talking about so far. And so what we're going to start with is with the following problem that is inspired by some things in the Nocedal and Wright book. So this is problem 1. So consider that you have the following data. And so here's your data. You have a time axis and a y-axis. And so you've collected some data at different times here, at m different times. And so you have m different measurements, y1, y2, y3, ... ym. And so let's say that these are some of the data points that you got, and that it had something like this, like ... going on in the middle here. So these are your measurements. y1, y2, ... ym, taken at times t1, t2, ... tm. And let's suppose that someone who is familiar with this data and with this process looked at the sum of all the data, looked at all of it and looked at the process, and they said that they think, someone said they think the process this system can be modeled as follows. So they think this system can be modeled by saying that there's this function phi of t and of some parameters x. So this is our time, but this is the model parameters that are yet unknown. And this is equal to x1 plus x2 e to the negative x3 minus t squared over x4 plus x5 cosine of x6t. So let's assume that someone said they think that this is the model of the process, and that once you get these parameters x1, x2, x3, x4, x5, and x6, and you fit them to the model with this structure, that they think it's going to be relatively predictive, so that if you have another time, they think you're going to be able, using this function, to guess the y value that you'll get at that time. They think that this is a good enough model. So let's say someone already said that. They said, I think this describes how y changes as a function of both time as well as being a function of some parameters I don't know yet, but once I fit those, x1, x2, x3, x4, and x5, and x6, then this model is going to do a good job of predicting what's going to happen at a given time. And so if this is the case, then we can say, okay, well, in order to get my parameters, so I'm going to make this vector of all those unknown parameters, so x1 to x6 in this vector, then I'll say, you know, I'd like to decide on those. So they're decision variables. And I want to find the parameters in this vector x such that yj is as close as possible to phi of tj with this x. So yj, which is the y at tj, is as close as possible to what the model predicts here. So this is essentially my predicted yj value at time tj with the model parameters at some x, that is what I'm going to try to find to make it so that when I use those model parameters x here, that then this phi is going to give me a really good approximation of yj at any time tj. And so we'll define this residual. Rj of x equals yj minus phi of tj given your x vector here. And this is going to be a residual from j is 1 to ... to m. And so what this does is it essentially is a measure of the difference between the measurement yj at tj and its predicted value from our model. And so since I fixed the model structure here, the question is what are x1 to x6 here so that I can get this residual as small as possible. And so as you can tell in some of the language that I'm using, things like how small can I make this, I'm probably going to want to minimize something related to this. And so specifically, I'm going to say, okay, I'm going to minimize over x in R6 because it's a 6-dimensional vector of real numbers. I'm going to try to minimize f of x is equal to r1 squared of x plus r2 squared of x plus ... plus rm squared of x. And so you can tell that this could even be a relatively challenging optimization problem, even if we just have no constraints. And that's because you can see, like, for example, if I have a lot of data points, this objective function will have a lot of terms. In addition, there might be potentially a lot of trade-offs among those terms as I try to minimize something with this kind of form. And so there might be a number of different local minima. And so the question that I'm going to ask, though, is the following. Say we just have 2 data points. That are t1, y1 equals 2 and 1, and t2, y2 equals 3 and 6. And so then this minimization problem that I've got up here is going to look a little smaller because I'm just going to have the residuals for 2 data points. So let's write this out a little more explicitly. This is minimize, find the minimizing values of x1, x2, x3, x4, x5, and x6. So these are all my decision variables, which can be in this vector x. So the vector x, you could also say it's the vector of the decision variables. So find the minimum value of, and let's write out our residuals explicitly. So it's y1 minus, and then we're going to subtract off what we would get for this if t was t1. So it will be minus x1 minus x2 e to the negative x3 minus t1 squared over x4 minus x5 cosine of x6 t1. And this is going to be squared because that will be the residual squared, which is this term, plus, and so this is still our objective function. Now we're going to do it for this R2 term right here. So y2 minus x1 minus x2 e to the negative x3 minus t2 squared over x4 minus x5 cosine of x6 t2 squared. And so you can see here our 2 residuals. So it's the difference between our model predictions and our measurements at both for corresponding to both data points that we have. And the reason I simplified this is not because you would really do this. I mean, you can already probably think in your mind that if you only have 2 data points and you fit 6 parameters based on 2 data points to see what gives the best fit, that probably this is not going to be a really well generalizing model. This is not going to have enough data for you to really be able to get these values of your decision variables, x1, x2, et cetera, up to x6 in a very good way. But what it does is it allows us to write some things by hand that can help show the way to use some of what we've been learning last time. So as we said before, when we have an optimization algorithm, we need to start with an initial guess. So our initial guess here of the values of the decision variables is x is equal to 1, 2, 3, 4, 5, 6. Let's just say I guess this. And when this is what our decision variables are, we can calculate the value of our objective function. So that's this. So this is our objective function f of x. And so if I do f of this, I'm going to call this xk to signify that it's the kth iterate. So in this case, it would actually be k is equal to 1. So it's the first iterate, but I'm going to call it that way. I'm going to denote this with xk. So here, f of xk, if I was to actually plug in this value of 1 for x1, for example, 2 for x2, et cetera, what you would come up with is you would get that f of xk is equal to 33.46319534000734. This is what I got from MATLAB. And I kept the digits here mostly because I'm gonna write some more things in a few minutes about like what are the what's the value of the objective function at a different point and stuff like that. So the question that we need to answer right now is to use a line search with the steepest descent direction to find a new iterate with a smaller value of f. So the idea is that I want f of xk plus 1 to be less than f of xk. And I want someone to show me how I could use a line search with the steepest descent direction to try to find this new iterate. So from last time, we demonstrated why the steepest descent direction is given as follows. So we said that our steepest descent direction is given by pk is equal to negative del fk over the norm of del fk. And if you're not sure why, go back and look at the lecture notes from last time or ask a question in the class. And then this is for the case that del f is equal to df1, oh, sorry, not df1, df over dx1, df over dx2, then you'll do all of them up to df over dx6. And when I write del fk, what this means is it means del f evaluated at xk. So it would mean if I got the derivative with respect to x1 and it's a function of some of the x's, that then I would plug in the xk that I have for those x's. So if I do this by hand and I go through, what I can get, I'm going to first define this thing. I'm going to call this T1. So I'm going to call this 2y1 minus x1 minus x2 e to the negative x3 minus T1 squared over x4 minus x5 cosine of x6 T1. And I'm going to make a similar one for T2. So it's going to be 2 times y2 minus x1 minus x2 e to the negative x3 minus t2 squared over x4 minus x5 cosine of x6 and t2. And so let me then write what the different partial derivatives are. So we're interested in the partial derivatives of f with respect to every one of the decision variables. And so for x1, it's just going to be negative t1 minus t2. For the partial derivative of f with respect to x2, it's going to be t1 times negative e to the negative x3 minus t1 squared over x4 plus t2 times negative e to the negative x3 minus t2 squared over x4. We get df over dx3 equals t1 times negative x2 e to the negative x3 minus t1 squared over x4 times negative 2 times x3 minus t1 over x4 plus t2 times, oh, I'm sorry, I forgot a negative over here, or I put it and it went away because sometimes this seems to erase things that I put. So if I didn't put it there, sorry about that. Negative x2 e to the negative x3 minus t2 squared over x4 times negative 2 times x3 minus t2 over x4, and df over dx4 here equals t1 times negative x2 e to the negative x3 minus t1 squared over x4, and then times x3 minus t1 squared over x4 squared plus t2 times negative x2 to the negative x3 minus t2 squared over x4 times x3 minus t2 squared over x4 squared. And then we have this df over dx5 equals t1 times negative cosine of x6 t1 negative cosine of x6 t2, and then you would get df over dx6 equals t1 times x5 t1 sine of x6 t1 plus t2 x2 t5 sine of x6 t2. And so for getting our del fk, we need to get del f at xk. So that means that in all of, if this stuff all makes up del f, we need to plug in our xk, which is this 1, 2, 3, 4, 5, 6. We need to plug that in to each of these expressions. And we also know that we're going to need the norm of del fk in order to get our pk as well. And so as a reminder, you can do something like df over dx1, and this is going to be at xk squared plus, and it will be df over dx2 at xk squared plus dot 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 plus df over dx6 xk squared. And so that's the two norms. And so from MATLAB, if I put in all those equations that I had and I plug in xk into them, it gives me this vector that del fk is 12.1569, 9.6012, negative 8.9981, 1.1248, 10.1480, and 68.7888. And it also gives me that the norm of del fk is equal to 71.812 to 9. So with those two things, I'm able to then get pk is equal to negative del fk over the norm of del fk, which is equal to negative 0.1693, negative 0.1337, 0.1253, negative 0.0151, negative 0.1413, negative 0.9579. And so this is our pk. And so good for us. So far we got our steepest descent direction. But then what we said is we want to do a line search. So we want to try to find an alpha that approximately does this. It should approximately get my f to be as small as it can go in this direction, pk away from xk. And so you could minimize this more exactly, but we're just going to settle for some approximation here to give the idea. So here's the idea. Let's try a few different ones. So let's try alpha is equal to 1e minus 5. Let's try alpha is equal to 0.1. It's equal to 0.5, and it's equal to 0.9. And let's look at what we get for f of xk plus alpha pk in each case. So in this case, I get 33.462477. In this case, it is 27.3066. Here it's 43.3634. And here it's 67.0236. And so among these, if I had to choose one of these ones, I would choose this one because this one made f of xk plus alpha pk the lowest of all of them. And note also that it does have, since f of xk is equal to 33.463195, that both of these that have the smaller values of alpha, these two, they're able to cause a decrease in the objective function. So because this is a descent direction, if I move some small distance in that direction, I'm able to get f of x to be a lower value at my new iterate xk plus alpha pk than I was at my prior iterate xk. And so here I'm going to say xk plus 1 is equal to xk plus, in this case, I'm going to do 0.1 pk and then say like, oh, okay, let's try that. And so that's some of the idea of how you would try to think about using some of what we did before as part of an algorithm. And so now we're going to look at another example. So this new example is an example in the convex optimization book. So this is example 4.5 in convex optimization by Vandenberg and Boyd. With like slight modifications to the way I'm asking it and framing it and stuff. So it says, what are the necessary and sufficient conditions for X star to be a minimizer of F0 of X is equal to 1/2 X transpose PX plus Q transpose X plus R, where P is contained in S plus N. So this is the set of symmetric, positive, semi-definite, n by n matrices. And so this is really an unconstrained quadratic optimization problem. So in this case, since it's unconstrained, what matters to us in determining necessary and sufficient conditions for X star to be a minimizer is going to be conditions related to unconstrained optimization. Now, something that's going to be important here is something that we did not cover before, but is a theorem that holds for the case that this objective function is convex and that we're doing unconstrained optimization. Now, it's going to turn out this is convex, but for a moment, let's just focus on this new theorem. So here's a theorem, and so this is going to be from Nocedal and Wright. So this theorem states that when f is convex, then any local minimizer X star is a global minimizer of f. And then if in addition f is differentiable, then any stationary point which is where grad f is equal to 0, X star is a global minimizer of f. So there's some pretty powerful things here. If f is convex and you find a local minimizer, it's also a global minimizer. So then in addition, if you have a differentiable f that's convex, then if you find a point where the gradient of f at a point is equal to 0, then it's also going to be a global minimizer. And so that's going to be part of this necessary and sufficient part. But first, let's look at the proof of this, because this is not super obvious. So we're going to have to prove both halves. So there's 2 sentences here. We'll prove the pieces piece by piece. So the proof goes that in the first sentence, let's do a proof by contradiction. So we're going to say, suppose X star is a local minimizer, so it meets half the conditions, but not a global minimizer. So if that's the case, then what would need to be true is that then there has to exist some z in Rn such that f at the z is less than f of X star, because that would be the idea that f of X star takes some value, but f of z is even lower. That's why f of X star is not the global minimizer. If it was the global minimizer, then there would be no other point that's doing better than it. So since we said it's not a global minimizer, there's some other point that minimizes the objective function more. Now, if X star is a local minimizer, that does mean that there has to be some neighborhood of X star over which X star causes f of X star to be its lowest value. But there could be some other point farther away where f of z is less than f of X star. It just can't be in the neighborhood of X star for X star to still be a local minimizer, but for this to hold true. So what we do now is then we say okay, let's consider the line segment joining X star and z. And so let's look at this case. So this is going to be x equals lambda z plus 1 minus lambda of X star, because that's how line segments work, with some lambda in 0, open to 1, closed, in this case. So then we say, okay, so what else can we say? So we know that f is convex, so f is convex, so its domain is convex set. And for any 2 p and q vectors contained in S, we should get that f of alpha p plus 1 minus alpha q is less than or equal to alpha f of p plus 1 minus alpha f of q for all alpha contained in 0 to 1. And so this is just a general statement about convexity. So for our problem, since f is convex for us, so for our proof, then we could take f at x, where x is what we said a minute ago, that it's equal to the lambda z plus 1 minus lambda x star for the lambda in 0 to 1. And so f of x is equal to, in this case, f of lambda z plus 1 minus lambda x star, which is then less than or equal to lambda f of z plus 1 minus lambda f of x star. So how do I know this? It's because f is convex, therefore this has to hold. And so this is just an expression of this convexity relationship. And then we would say, okay, well, you know what? Because f of z is less than f of x star, and the lambda here is between 0 and 1, this must mean that this is less than f of x star. So because this part over here would be less than f of x star strictly. And even if I was to have lambda be 1, for example, then now this would get 0 contribution, and this would be the full contribution, and this is a number that's less than f of x star. And then if I'm somewhere in the middle, like say this is half and this is half. So it's like, if this was equal to f of x star, I would add like half of f of x star and the other half of f of x star, and it would be equal to like all of f of x star. But it's not, because here I'm adding something less than f of x star. So for sure, when I add those two together, it's going to give me something that's less than f of x star. And so, okay, that means that we have this relationship that f of x is less than f of x star. And this is true for the different x that meet this requirement. So they're on this line between z and x star. And so the problem here is that any neighborhood n of x star contains a piece of the line segment between z and x star. So there are always points x contained in this neighborhood such that f of x is less than f of x star. And the problem is that for f of x star to be a local minimizer, this cannot be happening. There has to be no points in the neighborhood of x star such that f of x is less than f of x star, or else x star is not a local minimizer. So what we have just demonstrated then is that we've said that if f is convex, then any local minimizer must be a global minimizer, because either the local minimizer is a global minimizer or it's not. I only have two choices. And I was able to demonstrate that when it is a local minimizer, that if it was a local minimizer but not a global minimizer, then I would have a contradiction. So therefore, it should be a global minimizer. And so now we have to do the second sentence. So we have to say like, okay, this is really powerful. This tells me that if I have a convex function, that if I find a local min, I've also found the global min of that function, which is really great. But now let's add something else. So it says if f is differentiable, then any stationary point is a global minimizer of f. So, okay, so first we have to say what is a stationary point. And so a stationary point, so x star is a stationary point if del f of x star equals 0. And so this is also going to go by contradiction. So here we're going to say, suppose x star is a global minimizer but not a stationary point. Oh, sorry, I have this wrong. Is not a global minimizer, but is a stationary point. Then now we're going to need our directional derivatives. So now the mathematics that we learned the other day is going to start to become very relevant. So we're going to have to like talk through the directional derivatives a little bit more to make this next part make sense. But since people have seen this the other day, this should work out. So the idea is that the directional derivative of a function f mapping from Rn to R in the direction P is defined, here the notation that they use, which is a little different than what we used the other day because it's a different book. Here's the notation that they're going to use right now. So this means defined as equal to. Or I guess just like defined as. So defined as, it's like this. So this is defined as being, you could think of it as defined as being the limit as epsilon goes to 0 of f of x plus epsilon p minus f of x over epsilon. So it means that if I am going in this direction p, and then if I go some distance epsilon, I'm taking this limit as f of x plus this epsilon p minus f of x over the epsilon. And so something that we saw before is that if f is continuously differentiable, in a neighborhood of x, then what we get is that d of f of x p equals del f of x transpose p. So the directional derivative, this limit over here, actually becomes equal to taking the gradient of f at x and then transpose against this vector p, which is in the direction that we are trying to go. And so we talked about that last time, but here is how the Nocedal and Wright book talks it through, and that this is very important to understanding some of the steps that are in the proof. So I'm going to go over how they discuss it. So they say, okay, let's define this function phi of alpha, where alpha is like going to play this role of this epsilon. It's the step length. So it's f of x plus alpha p. And so I'm going to call this f of y of alpha, where y of alpha is equal to x plus alpha p. So assuming that the p is fixed and the x is fixed, then this y will be a function of the alpha. So it will vary with how we do alpha. And so that means that our phi here is a function of alpha, because as the alpha changes for a fixed x and a fixed p, we are going to modify the value of this f over here. And so we could say that if we take this limit as epsilon goes to 0 of f of x plus epsilon p minus f of x over epsilon. So notice that this is the definition of a directional derivative. In the direction p, directional derivative of f in the direction p. Then I could also write this as the limit as epsilon is going to 0 of phi of epsilon minus phi of 0 over epsilon. This would be an equally valid way to write it given the way I just defined p. And then we can look at this and say like, hey, look at that. It's actually equal to phi prime of 0 if I use normal derivatives for a case that phi is a scalar valued function of a single variable epsilon. And then, so then now we're going to need our chain rule. And so what we do at this point is we say, okay, based on the chain rule from before, say that I want to take the derivative of phi at alpha. So this is the derivative of phi with respect to, the derivative of phi with respect to alpha. And so the chain rule here is that this is really that phi is equal to f of y of alpha, and y is a function of alpha, which is x plus alpha p. So the sense in which we're doing the chain rule here is that we're saying, okay, if I want to get the derivative of this function f with respect to alpha, I need to first take the derivative of it with respect to the y's and then of the y's with respect to the alpha. So this is then going to equal the sum from I equals 1 to n of df of y of alpha over dyi times the del yi of alpha. And so the idea here being along these lines, that if I want to do d phi over d alpha, it's going to equal d phi over dy1 times dy1 over d alpha plus dot 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 plus d phi over dy, however many of these I have, I guess n of them, and then dyn over d alpha. So here's the idea. And so what I end up with here is that since y is equal to x plus alpha p, that then if I write this as every yi will be equal to xi plus alpha pi. So when I start to do these derivatives and I say, okay, what's my what's the derivative here? What are these terms? These are going to each be equal to the corresponding pi. So for the derivative of y1 with respect to alpha, it's going to give me p1 and so forth. And so what I'm going to end up with here from my chain rule is that it's going to be the sum from I equals 1 to n of df of y alpha over dyi times the corresponding pi, which we can see in this expression over here. And then we could rewrite this as del f of y of alpha transpose p, because we can see that if we do this out, it's going to give me this type of expression over here, which is going to be the derivative of my function phi, which is the f of y of alpha with respect to every decision variable, or sorry, not every decision variable, every y. And so that's going to make this gradient vector del f y of alpha, and then it's dotted against the pi's, and so those will form this vector p. And so this is then equal to del f of, now plug in for the y, So it's going to be of x plus alpha p transpose p. And so if alpha is equal to 0, then phi prime of alpha is equal to del f of x transpose p. Because that would be phi prime for alpha equals 0 is equal to del f of x plus 0 times p transpose p, which would be del f of x transpose p. So we can see that so we can see here that those are some of the relationships. And so this takes us back to our proof. Oh, and sorry, let me make this final point. This was the one that then connects up to here, which is the connection between saying that this, which is another definition of the directional derivative, is now equal to this, which is this part that includes the gradient. So that was the final connection here. There we go. Okay, now back to our proof. So back to the proof. Okay, so what we've got now is we're going to make this statement. So we're going to look at del f of x star transpose, and then we're going to have this interesting thing here, z minus x star. So you can think of this like a p. And so what is the idea here? What is z? So z is going to be the same thing as in the first half. So z is, again, in Rn, and f of z is going to be less than f of x star. And so why do I care about that again? Is because in this part of the proof, we are saying, suppose x star is not a global minimizer, but is a stationary point. So if x star is not a global minimizer, that means there is some point z that is the global minimizer that causes f of z to be less than f of x star. And so this is since x star is not a global minimizer here. And we still have f as convex, and we still have the same thing that we care about, it being convex. And so now we're going to note that this statement here is of this form, del f of x star transpose p. And so in what we just literally did, we said that del f of x transpose p is equal to the directional derivative over here of f of x plus epsilon p minus f of x over epsilon, that type of thing. And so we can say, oh, okay, this is also equal to the change in f at some x plus some distance times my p when the lambda is 0. So this is going to be equal to my directional derivative here. So it's the limit as lambda goes to 0 of f of x star plus, and then making analogy back here. So we've got to write some type of interesting epsilon-like thing here. So here we're going to use lambda times my p, so z minus x star minus f of x star over lambda. And so again, making the direct analogy, this thing, we have it at x and the p is some direction, then if we have some distance in that direction, then this is going to be equivalent to the directional derivative, and then you see that right there. And so now we're going to make some statement that this is actually less than or equal to the limit as lambda goes to 0 of f of lambda f of z plus 1 minus lambda f of x star minus f of x star. And so this is coming from convexity. So this is coming that we use the convexity requirements in order to transform this part that we have right here into a form that is appearing in the second equation. And then this is going to equal f of z minus f of x star. But then from our assumption that, that I wrote over here, f of z is less than f of x star is what we're assuming right now, because we're saying like, oh, there must be, let's say that x star is not the global minimizer, then the global minimizer is out there. And then this is less than, in that case, 0. It's less than 0, because if this is true, then if I subtract f of x star to the other side, this will say f of z minus f of x star is less than 0. And so this is from our assumption that x star is not a global minimizer. And then so at this point, we say, oh, okay, well, problem. If this is true, this means del f of x star transpose of z minus x star is less than 0, but we said del f of x star is equal to 0. So this is a contradiction, because it can't be both less than 0 and equal to 0. Oh my goodness. Can't be both less than 0 and equal 0 at the same time. And so if this was true, what this would mean is that therefore x star is not a stationary point, which we said it was. So proof by contradiction. Okay, great. So let's go back to our example then. So going back to the example, and so what I mean by that example is the one where we said what are the necessary and sufficient conditions that we need here. So what we see then is that one, any point, or let me write the other thing. Here's a necessary condition from the first order necessary conditions that we did last time. A necessary condition is that if x star is a local minimizer and f is continuously differentiable, in an open neighborhood, of x star, then del f of x star is equal to 0. So this was a first order necessary condition. And then just now we got a sufficient condition, which is that if del f of x star equals 0 and f is differentiable and convex, where convex is a very important part of this, then x star is a global and local minimizer of f. And so what this means is that the necessary and sufficient condition that we're looking for, if f is a convex function, and if f is a convex function and differentiable, then what we want is we want this condition. Then we want the condition where del f of x star is equal to 0, because that's going to be our necessary and sufficient condition for this function to demonstrate that it is a local min. And so in this case, we have to say, is our f convex? And so to remind ourselves what this means is that its domain S must be a convex set, meaning that for any xy in S, alpha x plus 1 minus alpha y is in S for all alpha in 0 to 1. And then also for any 2 points x and y in S, then f of alpha x plus 1 minus alpha y is less than or equal to alpha f of x plus 1 minus alpha f of y for all alpha in the range of 0 to 1. And so these are the things we would have to test. And so our f right now is the one where it's the f0 of x is equal to 1/2 x transpose p x plus q transpose x plus r, where the p is in S plus n. So then first we can say, like, what's the domain of this? So the domain is Rn. And so we could say, oh, does it meet this condition that essentially I add together? Like I make some linear combination of 2 points in x and y, where this linear combination has to be a very specific type, like the alpha has to be between 0 and 1, and it has to be like this. We say like, oh yeah, well, Rn is actually a vector space. And so if I make any linear combination of any 2 vectors in the vector space, it gives me back a vector in the vector space. So we already know that, like, oh yeah, for sure, the domain is a convex set. So the domain is Rn, convex, yes, due to being a vector space. And then we could say then, like, oh, okay, what about the second part? Like, do we satisfy this thing? And so what I'm gonna do is I'm gonna say, like, check the convexity condition. And to be able to see it, what you should do is you should go back to the lecture where we were proving that f of x equals x transpose hx with h symmetric positive definite or positive semi-definite. Is convex, and use that and try out that idea to try to finish the proof here. So the main point that what you're going to find is that f0 is convex once you do that. And so then we need to say therefore the necessary and sufficient condition for x star to be a minimizer of f0 is that the gradient of f0 at x has to equal 0. And so then we can say, like, okay, so what does that mean for this objective function? Like, how can I write the gradient of f0 of x? Well, you can convince yourself that it takes the following form. So the gradient f0 of x is equal to px plus q. And so this would have to equal 0. So this is a condition that we're looking for. But so you say, how do you know that? Okay, so you can convince yourself of this by writing it out. So remember that this matrix P is symmetric right here. So what this means is that like the P12 is like reflected over the diagonal. This will go to P1n and this will go to P1n and so on and so forth. And you can fill out all the entries in here. And then this will be x1 to xn. And then we'll say plus q1 to qn. And then x1 to xn plus r. And so at this point, you can then do, like you can start making the multiplication. So this will be like 1/2 times x1 to xn transpose, and then you will start to get these two multiplying each other. So you can have p11 x1 plus ... plus p1n xn, and then ... and you can have p1n x1 plus ... plus pnn xn plus, and then if I actually do this dot product right here, or this inner product, q1 x1 plus ... plus qn xn plus r. And so then if we finish this out, what we would end up with is we would get something that has like equals 1/2. We'll have like a p11 x1 squared plus, and there'll be like lots of terms, p1n x1 xn plus ... plus another p1n x1 xn due to the symmetry in this matrix, which is what causes the p1n to appear twice. And it will go like on and on and on. And finally, you get like this type of thing. And then plus q1 x1 plus ... plus qn xn plus r. And so you'll need to look for patterns at this point to help yourself really see this. And so if you can't see what's going on, write more terms and see the patterns in them. But then now we need to take the derivative of this. So you would take the derivative with respect to every one of the decision variables. And so let's just take it with respect to the first one. And you could take it with more to see the pattern. But you will see that this one will get to be like this. And then these other ones that are the same as each other will like sum together. So you'll also get ones that are like plus 2 p1n xn type things. And then plus here, only this term will survive when I take the derivative with respect to x1. And then there's the derivative of the r, since it's a constant, is just going to be 0. So we can see that this ends up being p11 x1 plus ... plus p1n xn plus q1, which you could write this as being like p11 to p1n x1 to xn plus q1. And so we can see that this sort of looks like the first column of p. And so as it turns out, if you take all the rest of these derivatives, you're going to progressively build all the columns so that when you make this full gradient vector, del f0 of x, that you're going to be able to get every one of these entries in the gradient vector by setting del f of x0 equals px plus q and say that's equal to 0. So convince yourself of that if you don't see it. Okay, so now another example. So this is our third example. So rewrite an optimization problem. That's what this one's about. So here it says, consider the problem to minimize f0 of x subject to the following constraints: fi of x less than or equal to 0 for I equals 1 to m, and hi of x is equal 0 for I equals 1 to p. And so the question is to rewrite this optimization problem in a form that has the same optimal value of x but with the inequality constraints replaced by equality constraints and non-negativity constraints. So as we mentioned in one of the lectures last time, we said that many times you can rewrite optimization problems so that you can write them in a new form that has the same optimal values of your decision variables. So it's essentially equivalent. And so this one is an example of asking to rewrite it, right? This original one in a form where you replace your inequalities with equalities. And so this is actually something that's very common in optimization known as slack variables. And so the idea here is to note the following. So if you have fi of x is less than or equal to 0, that's your like first constraint right here. This is true if and only if there exists some si greater than or equal to 0, such that fi of x plus si is equal to 0. So note that what this means is that I have some margin that since it's positive, it means that fi is less than 0. So I have to add a positive number to fi in order to make fi plus this positive number equal to 0. That means that fi has to be less than or equal to 0. And so recognizing that this is like the same thing, that fi less than or equal to 0 is the same as saying that there exists some si greater than or equal to 0 such that this holds true, we can replace our constraints. So we can say, okay, minimize over s in Rm and x in Rn. So now we are increasing our number of decision variables because we're adding these slack variables. So these are the slack variables. And it will say f0 of x such that si is greater than or equal to 0 for I equals 1 to m. So this is a non-negativity constraint. So that's this one right here. And then we have fi of x plus si is equal to 0 for I equals 1 to m. And so this is replacing my inequality with an equality constraint. So far I replaced my inequality constraints with two that are non-negativity and equality. So I did what the problem statement said. And it also says hi of x equals 0 for I equals 1 to p. And so at this point, we increase our number of decision variables. So in our original problem here, we only have n decision variables. But over here, because I add the slack variables, the s variables, now I have n plus m decision variables. And up here, I had m inequality constraints. But here I also have m inequality constraints. But these ones are the non-negativity constraints on the slack variables si for I equals 1 to m. And then up here, I've got p equality constraints. And down here, I have m plus p equality constraints. And so this new variable, the new variables si are the slack variables. And they're associated with the original inequality constraints. Fi of x is less than or equal to 0. And so here is my transformed problem as required. And let's just make a few comments. So these two problems are actually equivalent in the following sense. So they are equivalent in a number of ways. So for example, if x and s is feasible we call these 1 and 2 for a minute, is feasible for 2, then x is feasible for 1. Oh, okay. X is feasible for 1. And specifically, it would be with SI equals negative FI of X needs to be greater than or equal to 0. And so we can see here that if X and S are feasible, this implies already that FI of X is less than or equal to 0 through this. So that would be this constraint in the original. And then we also are going to have that if X is feasible in the original, then there is an XS with the same X and with an S that's feasible in the second one, where the SI is equal to negative FI of X. And the final thing that we have here, which I'm running out of space, but I want to put these in order and on this slide if possible, is that if XS is optimal for for 2, then X is optimal for 1, and vice versa. So in this sense, they're equivalent. They'll give you the same solutions. So in either case, our objective function is still only dependent on X. So whatever X is able to minimize both of these objective functions should give us the same optimal value of the objective function. And then in both cases, since these constraints are really equivalent, we should be getting the same answers in both cases. So that's a case of rewriting an optimization problem, transforming it from one way to another way, where then you're able to have some equivalence between the problems in terms of getting the same optimal values of your decision variables, or the same final, the same solution to your optimization problem. And so now we just have a few more points to make in our example. And so finally, what I want to do is like a fourth problem here. And so this one is about the linear independence constraint qualification and some of the KKT conditions, and trying to start to see how those play out and what's the significance of these. So trying to make a little bit of sense of our beginnings of our constrained optimization lecture. So as a reminder, the first order necessary conditions for a constrained optimization problem are going to, you can have some of the following. So suppose that X star is a local solution of this problem. So minimize over X in Rn f of X such that Ci of X is equal to 0 for I in E, and that Ci of X is greater than or equal to 0 for I in I. And so we're going to suppose that X star is a local solution of this. In addition, that F and Ci are continuously differentiable. And finally, this part, the Li CQ, the linear independence constraint qualification, holds. And so these are my assumptions right now. And so if that's true, then there is a Lagrange multiplier vector lambda star with components lambda I star, I contained in E union I, so that's the union of the indices for the equality and the inequality constraints, such that the following conditions are satisfied. At x star and lambda star. And so this will say that del x L of x star lambda star equals 0, Ci of x star equals 0 for all I in E, Ci of x star greater than or equal to 0 for all I in I, lambda I star is greater than or equal to 0 for all I in I, and finally lambda I star Ci of x star is equal 0 for all I in E and I. And the LICQ, just to remember what that is that given the point x and the active set A of x, we say that the LICQ holds if the set of active constraints, active constraint gradients, which is the gradients of the constraints that correspond to the index being in the active set, is linearly independent, which we know what that means from our linear algebra. But as a reminder, what's the active set? Is that the active set A of x at a feasible x consists of equality constraints, so equality constraint indices from E together with indices of the inequality constraints I, for which Ci of x is equal to 0, meaning that A of x is equal to E, and then the union with I contained in I, such that Ci of x is equal to 0. So these are the reminders of some of the definitions we went over last time that are relevant to what I'm gonna do right now. And so, but just as like a reminder then, why we would care about these things is, say for example, that we want to be able to write out, so like say x star is a local solution, then I want to be able to write out what are the things that are gonna hold when I reach x star. Like I want to be able to write out and say like these things are going to hold for my optimization problem at x star. But I can't just write this out anytime, like just because I say, okay, there's a local solution, but if the LICQ doesn't hold, then this doesn't necessarily follow that all of these things are true. So I would need to say like, okay, if f and ci are continuously differentiable and if the LICQ holds, then when x star is a local solution, the following things are going to happen. And so it's nice to be able to write out these types of optimality conditions and say like, okay, if this is a optimum, here's what's going to be true. But there's this kind of barrier right here that we don't really quite understand yet, the LICQ. And so what we need to do then is look at some brief examples. And so let's say that we have this optimization problem. So we're going to maximize over x1 and x2 some function f0 of x1 and x2, such that, let's say that we have x1 plus x2 is less than or equal to 5. And then that we have x1 is greater than or equal to 0 and x2 is greater than or equal to 0. And so first I'm going to put this in the form that is over here. So this type of form, which has, when I have these inequality constraints, it has them be greater than or equal to 0. And then also I have a minimizing objective function. So remember that when you maximize a function, it's the same, you get the same optimal, you get the same solution in terms of you get the same decision variables solving this problem if you minimize the negative of this function. And then, so such that, and so like we just said, what we're going to do to get it in this form is that the constraints are going to be greater than or equal to 0 here. So it's going to be such that 5 minus x1 minus x2 is going to be greater than or equal to 0. And then we have x1 greater than or equal to 0 and x2 greater than or equal to 0. And I'm going to call this one C1. I'm going to call this one C2. I'm going to call this one C3. So now what we have to do is we have to be able to say like, okay, let's look at what's going on with the LICQ. So it says that in order to look at whether or not the LICQ holds, that I need to look at my active constraint gradients and check if they're linearly independent. So first, let me just get the gradients of all of these constraints. So the gradient of the first constraint with respect to x1 and then with respect to x2. So this one's just going to give me -1, -1. And then the gradient for C2, here's my gradient for C1. My gradient for C2 is going to give me 1, 0. And my gradient for C3 is going to give me 0, 1. And so now we don't know where our optimal solution is right now. So right now, I don't know like where it's going to be. So when I just say like, okay, depends on which constraints are active at my optimal solution. So like, okay, well, I don't know where the optimal solution is. So instead, let me just like think through the different combinations of what could possibly happen. So at my optimal solution, many things could happen. So many possibilities since I don't know the optimal solution yet. So I could have only maybe that C1 is active. I could have that C2 is active, meaning that it's in the active set. So like C1 is literally equal to 0, C2 is equal 0, etc. So C3 is active. I could also have that C1 and C2 are active. I could have that C1 and C3 are active. I could have that C2 and C3 are active. And I could also have the condition that what if they were, what could they all be active at once? C1, C2, and C3 be active. Okay, so then we need to go through and say like, okay, regardless of which possibility it is, am I going to get all of my, my active constraint gradients? Are they going to be linearly independent? So first, let's handle this one down here. So note that if C1 and C2 are active, that means that these two constraints are satisfied with equality. So this would mean that x1 is equal to 0 and x2 is equal to 0. And so if that's true, then C1 is equal to 5 minus 0 minus 0 is greater than or equal to 0. Now, it's clearly not going to equal 0 if x1 and x2 are equal to 0. So these are not going to be all three active at once. So I'm not going to consider that. They're not going to be all three active at once because this is not going to happen. This is going to definitely be greater than or equal to 0. It's not satisfied with equality if x1 and x2 are both 0, which would be if C2 and C3 are both active. So then let's look at the other cases. So if C1 is active, then is this gradient like linearly independent? Okay, sure, fine. If C2 is active, is it fine? Yeah. If C3 is active, is it fine? Yeah. It's a linearly independent vector. That's fine. Okay, so now what if C1 and C2 are both active at once? So are these two vectors linearly independent? And the answer is like, yes. Okay, then what about C1 and C3? So what if these two are active at once? Are these linearly independent? Oh, yes, they are. Okay, what if these two are active together? Okay, yes, they also are. Okay, so the LICQ here is going to hold. And so let's look at an example where it doesn't hold. So this is coming from these notes. So it's Montes Oka.com, teaching UD S14 math. This is going to be 529-10, session 13, handout.pdf. Okay, so here I'm going to take an example from this. And so it says, okay, let's do the following. What if we have to maximize x1 such that x2 minus 1 minus x1 cubed is less than or equal to 0, and x1 and x2 are greater than or equal to 0. And we're going to ask if, does the LICQ hold at x is equal to 1, 0? And so, because you can see here, like given the point x and this active set at x, we say that the LICQ holds if the active constraint gradients are linearly independent. So right now, we're going to look at our x is going to be this 1 and 0. And so the first thing then that you have to do to use the LICQ, like of course, first we should probably put it in the right form up here. So we're going to change this to minimize negative x1 subject to, and then we're going to make sure that we have all of our constraints are in the right, are in the form that the book was considering. So we're going to say any inequalities should say they're greater than or equal to 0. So here I can easily accomplish that. I can say 1 minus x1 cubed minus x2 is greater than or equal to 0, that x1 is greater than or equal to 0, and x2 is greater than or equal to 0. And then we call these again C1, C2, and C3. And so then we have to say at x equals 1, 0, what's the active set? Because I need to look at the gradients of the constraints that are in the active set. So what's the active set? So this will mean whenever my constraints are actually equal to 0. So right now, I would need to say like, okay, let's look at C1. So at this point 1, 0, let me plug in what this would be. It would be like this. And so this constraint is actually equal to 0. So C1 is active at 1, 0. And then let's look at the second constraint. So at this would give me x1 is equal to 1, which is greater than or equal to 0. So C2 is not active at 1, 0. And then finally, we get this one where we say x2 is 0, which is equal to 0. So C3 is active at 1, 0. So now that we have our active set, now we need to get the gradients of the constraints that are in the active set. So we need the gradient for C1 at x. We need the gradient for C3 at x. We need to look at whether or not these are linearly independent. And so the gradient for C1 at x, let's just write it in terms of a general x for a second, and then we will plug in the correct value here. Okay, and then 1. And so now we're evaluating it at x equals 1, 0. So this is going to give me 0, 1 when I actually plug that in. And now, so let's do the gradient of this one. So this is also 0, 1. And so, oh, look at that. These are not linearly independent. So we have that the LICQ does not hold at 1, 0. And so that's the notes for today. Hopefully that gives you a little bit of a better sense of how optimization, like some of the theory we've been learning, could play out in actually trying some examples. And then also, I guess I should make the note, like, what is the point of all of this? Like, why do we care about all of this? Well, the point is that a lot of this theory, the benefit of it is that it can be used in designing algorithms. So I think this first problem here starts to give some idea of how you could start to try to go about saying, like, okay, let's try to build an algorithm that actually tries to systematically find the values of my decision variables that minimize the objective function. And I think we can see from last time that we are trying to build toward things that are helpful in algorithms as well through doing these constraint qualifications, different like necessary and sufficient conditions, because I think, like, you can see in this second example that we did here with the convex optimization problem, we were able to write out a sufficient and a necessary condition for X star to be a minimizer. So this would mean that if there is an X which satisfies this equation, now I know that it's a minimizer, because satisfying this equation is both necessary and sufficient for X star to be a minimizer of my objective function. So what this does is it kind of reframes my original optimization problem. So instead of solving something written as like minimize this, instead you have to solve this system of algebraic equations that says, okay, find the X that makes Px plus Q equals 0. So you could write that as Px equals negative Q, and it becomes solving a system of linear equations, which is something that we've already done in linear algebra. And once you find the solution to this system, now you have the minimizing X star. And so you can see that the different mathematics of this, even though a lot of it feels like a lot of math, what it's doing is it's building toward how do you actually design algorithms so that when you have these different types of problems that we encounter in engineering, things where you want to make something the best, and you want to find something that is the best solution you can, but subject to different requirements that you have, that then if there are algorithms that exist for allowing you to actually solve those problems in an efficient way using a computer, then that is a tremendous benefit for so many engineering calculations, because the number of things that we try to optimize is so immense. You can be, I think, like we've said before, you can be optimizing like your, you can be having an optimization-based controller that's trying to find the optimal inputs to the process. You can be trying to find an optimal process design that minimizes your costs while meeting certain requirements, like on purity or specifications that you might have for flow rates and things for your customer. You might be interested in trying to find the electronic configuration, which it minimizes the energy for your for like some type of atomic system. You might be interested in minimizing Gibbs free energy, and just so many different things that we can come up with in engineering involve minimization and or maximization, and trying to do the best decisions that we can. And so seeing where algorithms come from and a bit of the mathematics that lies behind their design is incredibly useful. There's also a ton of use of optimization and machine learning, and just like I feel like, wow, like optimization is just so critical for any engineer these days. And to have some understanding of where algorithms come from and some of the mathematics behind it can only make you more capable of reading the literature and of reading things that become important to you along the way as you try to better understand how things work, and then also the numerical issues that can come about. And so if you understand where algorithms come from and some of how they're structured, you can start to understand even numerical issues. So like a lot of times, if you just try an optimization algorithm, it doesn't work out like exactly like you would hope. Sometimes problems can be a little harder to solve. And if we look at this example, we start to see how understanding the algorithms gives us some insight into why what we try does or doesn't work. And so, for example, in this example right here that we have, some of what we can notice is that like some of the things we mentioned earlier with regard to having enough data So like, if I don't have enough data, by seeing exactly how this works algorithmically and what it looks like mathematically, we can see like, oh, wow, like, yeah, what I'm literally doing is finding these decision variables that minimize this residual, but they're just minimizing this function. I mean, they're just finding values that make this function as small as it can go. They're not universally